Hi, everybody. Last time we looked at the central limit theorem for the first time and used it to approximate some probabilities involving some distributions of continuous type. Now I'm going to show you how you can use central limit theorem to approximate probabilities for distributions of discrete type. It's really the same thing with a slight little twist due to the discreteness. So to bring up an example, think about binomial distributions. You know, we know that a binomial with n trials is the sum of n independent Bernoullis, each with chance p of success. So it's the sum of a random sample. And so if the sample size is large, central limit theorem says that the distribution should be about normal. So it's saying that the binomial NP should be about normal with a mean equal to the mean of the binomial NP and the variance equal to the variance of the binomial NP1 minus P. Now, how big should N be for the approximation to be good? The textbook says that the expected number of successes, NP, and the expected number of failures, N times 1 minus P, should be at least 5. You'll see other people say that those two quantities should both be at least 10. I don't want to really fight about which one's right, but I'd like to do some investigations to convince you why it is that they want both the expected successes and the expected failures to be at least a certain size. So we do that with a function called binom skew out of the TigerStats package over in R. Let's head to R, and first thing I'm going to do down here is I'm going to library TigerStats here in the console, so have it around. Okay, coming up. Now let's do binom skew, and you should be following along. And I'm going to have to kill my face. Well, no, can I move my face? Yeah, I'll move my face. So yeah, I'll kill my face. I'm going to make this bigger. Make it easy to look at. So what we're looking at right now is the probability mass function for a binomial random variable with 50 trials. You can vary the probability of success. And if you click this little clog, you'll see that the chance of success right now is set at 0.01. And so the little stick probabilities go together to show kind of a right skewed distribution. Now we're computing the expected successes, n times p, and the expected failures, n times 1 minus p. And right now the expected successes is pretty low. If I were to make a normal curve that has the same mean and variance as this distribution, there's not a lot of resemblance between the two. But if you go into your success chance and bump it up to like 0.02, 0.03, 0.04, then you're going to bump up the expected number of successes. And by the time the success chance has gotten to 10%, the expected successes, 50 times 0.1, is 5. The expected failures has been big all along. And look, the shape of the PMF is kind of close to normal. Stricter people say that you should have at least 10 expected successes and failures. If you bump the chance of success up to a 0.2, you'll get 10 expected successes. And by now, the shape is looking really close to normal. Okay, but why do you also concentrate on expected failures? Well, what if the chance of success were really high, like 0.99? Then the PMF would be skewed left the other way. Big sticks, then not so big sticks, going off to smaller numbers. But once again, if you were to drop the chance of success, then you can increase the chance of failure, thus increasing the expected failures. And here I'm getting up to chance of success being 80%. Now the expected failures is up to 10. Both quantities are at least 10. And I'm looking at a distribution that looks a lot like a normal curve. So that's why they say what they say. Okay, I'm going to get out of this and go ahead and smallify this graphing window again. And back to the notes. So let's apply this. Let's approximate a binomial probability using the central limit theorem. So we need to set up a binomial random variable. Say you flip a fair coin 100 times, you're counting the number of heads. And you want to find maybe the chance of getting anywhere from 45 to 55 heads, including the 45 and the 55. So X is a binomial random variable, 100 trials, chance of success 0.5 each time. So the expected value, NP, is 50. The variance, NP1 minus P, turns out to be 25. Standard deviation, therefore, is 5. Flip a fair coin 100 times, you expect 50 heads, give or take 5 or so. Okay, central limit theorem says that X is about normal, mean 50, variance 25. So let's see if we can get this probability. Well, I'm going to do something a little funny at first. I'm replacing the 45 with a 44.5 and the 55 with a 55.5. I'll explain why in a minute. But I do want to convince you right here and now that that's an equal sign. And the reason is that X is a discrete with only whole number values possible. So there's no way for X to turn out to be anything between 45.5 and anything between 44.5 and 45. And so the chance of being bigger than this number is the same as the chance of being bigger than equal to this number. Similarly, the chance of being less than or equal to 55 is the same as the chance of being less than or equal to 55.5. The discreteness of X is making that true. So I'm not changing my probability when I make that move. Nor am I going to change my probability when I subtract 50 from all three sides of that inequality and divide all three sides of that inequality by 5. The event's the same, the probability is the same. But what I've got now is X minus its mean over its standard deviation in the middle. And the central limit theorem says that's approximately a standard normal. So if I replace it with something that's exactly standard normal, I should get about the same probability. And so here I am looking at the area under a standard normal curve from minus 1.1 to 1.1. And you could go to R and you could work on that. P norm at 1.1 minus P norm at negative 1.1. And it comes out to 0.7286679. Now, we know that we can get binomial probabilities more exactly by using P binom. So I could do P binom at 55, size is 100, prob is 0.5, minus P binom 44, because I want the chance of 55 or less minus the chance of 44 or less. Include, so that way I can include the 45. And I come up with almost the same thing. I mean, they differ in the 4th decimal place. So this approximation is really great. But what made it great was that little funny move. So why did I do that? Why did I do the switch? It could help if we got a graph of the probability mass function in its probability histogram form. So I'm going to use P binom GC over in R. I'm going to run this command, except I'm also going to add a graph equals true so we can look at the PMF. So let me head to R and give this a try. So P binom GC, concatenate from 45 to 55. Size equals 100, prob is 0.5. The region, I've got to remember to say, is quotes between. And I want graph equal to true. And let's run that. And we get this picture here, which I will maybe zoom in on. Oh, wait. Yeah, okay. So I'm okay. So zoom in on this. So the probability is the sum of the areas of those little rectangles. Each rectangle is centered over a possible value of the binomial random variable, and each rectangle has width 1. The height is the probability of getting that value. To get that area, to get that probability from 45 to 55 heads, you need all of those rectangles included. Now, think about the normal curve that approximates this. So it's kind of like running along the tops of these rectangles with my mouse there, okay? Can I make that? Yeah. Ooh, no, I can't do it. Yeah, there we go. So imagine that normal curve running through. If we really want to use that normal curve in the best way, then we need to be looking for the area of that normal curve, or area under that normal curve, starting from the beginning of the 45 rectangle and going to the end of the 55 rectangle. Then I'll come close to the blue area of all those rectangles there. So I have to go back to 45 and a half, and I have to go up to 55 and a half. That was the reason for my move. If I'd have stayed at 45 and 55, I would have missed half the 45 rectangle and half the 55 rectangle. I would have missed a substantial amount of probability. Not good. So that's why we do that. So including all the rectangles you want to include is called the half-unit correction for continuity. The normal curve is continuous. The random variable whose probabilities you're trying to approximate is discrete. You've got to correct for the fact that you're approximating a discrete with a continuous random variable. So make sure you do that in other probabilities involving discrete stuff. Like if you need the chance of less than 43 heads, then you want to include the chance for everything up to and including 42 heads. So make sure you include the 42 rectangle. Or if you want the chance for bigger than or equal to 47 heads, make sure you include the 47 rectangle. If you want the chance of 50 heads, make sure you include make sure that you get the 50 rectangle. So you got to go to from 49 and a half to 50 and a half. And then you would get the chance of 50 heads approximated. Let's try another example. Let's say the number of trees in any acre of forest is distributed as Poisson with a rate of 60. So that means the expected number of trees in an acre is 60. The variance is 60. That's how Poissons are. The mean and the variance are both the lambda parameter. And let's say you're going to walk through 100 acres and count the total number of trees. So you can think of that as walking through acre 1, counting the trees, walking through acre 2, counting the trees, and just keep on moving left to right through your acres, counting the trees, and then adding them up. Okay. So you can think of this x as the sum of a random sample of size 100 from an underlying Poisson distribution. Well, 100 is a big sample size, so maybe we could use the Central Limit Theorem to estimate probabilities for x. Like, what if we wanted the chance that the total trees is between 5950 and 6100? Well, if we use the Central Limit Theorem, then we say that this sum of 100 samples is about normal, with mean equal to 100 times the mean of the underlying distribution and variance equal to 100 times the variance of the underlying distribution. And so when you apply the Central Limit Theorem, you're going to want to make sure to include the 5950 rectangle. After all, Poissons are discrete. They're possible values of these whole numbers. I got to include the entire rectangle over 5950. So I'm going to go back to 5949.5. You also got to include the entire 6100 rectangle. So you're going to go up to 6100.5. You're going to make those moves of subtracting off the mean and dividing by the standard deviation. And so I've made those moves here so that what's in the middle is about standard normal. And then we could head to R and we could try to, find this probability using some P norms. So let's head to R and just do that. That's some fairly extensive calculations, so I brought up an R script to give it a try. The lower was 5949.5 minus 6,000 over the square root of 6,000. Let me compute that. There it is in the global environment. Yep, there we are. The upper is 6100.5 minus 6,000 over the square root of 6,000. There's the upper. And then I want the chance of being less than or equal to the upper in a standard normal. So that's my P norm. Upper, mean is 0, SD is 1. And I'm just going to call that U for short. Okay, I've got that chance. It's about a 0.90. There it is in my global environment. Now I'm going to get the chance of being less than or equal to the lower bound, call it L, and that's about 0.25. And so if I subtract the two, I get about 0.6455457, about a 64% chance. Of course, we know the distribution of X exactly. It is the sum of 100 Poisson 60s. And we know that the sum of independent Poissons is again a Poisson, where its rate is the sum of the rates. Well, we've got 100 with rate 60. Some of that is 6,000. So X is Poisson with rate 6,000. So I could find my probability more exactly like this. Chance of a Poisson to be less than or equal to 6,100 when the rate's 6,000. Minus the chance of the Poisson to be less than or equal to 5949. That way I can include the 5950. So if I just find that difference, okay, well, again, I get about 64%. The approximation is really, really good. So the little continuity correction can be very, very important. So back to the notes. You might be wondering, like, why do people use the central limit theorem to approximate anything when the computer can give you quote unquote exact values for so many of these distributions? And even if you didn't know the distribution mathematically, so that there was no computer program written by anybody to give you exact probabilities, couldn't you like do some simulations to estimate probabilities? Well, yeah, you can do those things. But the central limit theorem is so important in stats theory that it's really important to learn how it's applied. And the other thing is, frankly, a lot of these so-called exact routines in computer programs to find probabilities for these random variables, a lot of them are going to rely on the central limit theorem in order to deliver good approximations very quickly. I bet that's the case for some of the programming behind some of these P-Poissons and P-Binomes. Who knows, that might very well be the case. So the central limit theorem is of just crucial importance in probability and in statistics. That's about all I got for this section. See you later.